Okay, great. All right. So, my name is Tip. Thanks for the introduction. I'm from Chula in Bangkok, Thailand. And I've been thinking about the intersection of statistical mechanics and learning algorithm, and recently applied to understand quantum machine learning algorithm, which is the topic of today's talks. And the goal was to really thinking of whether quantum advantage could arise in quantum machine learning tasks. In other words, is it really worth building this fancy chandelier-like looking quantum devices for information processing, specifically for machine learning tasks? So I'll be telling you about two frameworks. One is quite well established, called Variational quantum algorithm, and I will tell you about the problem with scaling up the system size and get quantum advantage from the usual Variational quantum algorithm framework for machine learning. And then in the second part, I'll switch to more technical talks for non-variational framework, some of the quantum machine learning algorithm, based quantum reservoir computing and quantum extreme learning machines. So the first part would be some sort of high-level tour of what people in quantum machine learning community have been thinking about in terms of scaling up the system size and hopefully attain some quantum advantages. What are the bottlenecks for scaling up, and how do we bypass that, and what are some of the open problems? And on the second part, I'll introduce kind of new models and tell you how you might think about scaling up quantum machine learning with potential quantum advantages. So if you have any questions in between, feel free to just unmute yourself and ask. I cannot see any of you now because my screen is fully on the slide, so I don't know if I'm speaking to myself or not. So if you have any question, just ask right away. You can hear me all right now, okay?
Yeah.
Okay, all right, cool. So I'll move forward. So as I said earlier, I've been working at the intersection of these three fields. I was trained as a statistical physicist and been applied these tools to understand what is the fundamental building blocks of learning algorithm from complex system viewpoints, and recently applied these tools and techniques to study many body quantum physics, quantum information. So as a result, quantum machine learning is one of the natural intersection between these three fields. And here's the picture of my university. We are in July Intelligent Systems Lab with the acronym called CHICS. If you happen to be in Bangkok, I would be happy to host. So just text me and let me know. And one of the themes at these three intersections that I have been thinking about the past few years was try to think about how many body systems where there is a quantum dynamics, where interactions between microscopic degrees of freedom of spins or qubits could give rise to information processing at the larger scale. In the physical scale, you could have a variety of neural networks. Each of the fundamental units is no longer quantum bits, but now neurons. They can work together if they are firing in certain patterns, or they are coordinated in certain ways due to activities and network effects. You could get artificial intelligence as an inspiration that comes out of studying biological neural networks. And at the population levels, there are information sharing among individuals, and that could lead to the studies of emergent collective intelligence in society and so on and so forth. But all in these scales, because it's the many body effect, fundamental effects such as chaos and noise are ubiquitous in all scale. You could have quantum noise at a microscopic level. You could have fluctuations in voltage activities of neurons, or even you can even have the noisy signals from communications with your peers at the population levels. And all of these influence the collective information processing. So one of the themes that I've been thinking about that you see later on in the second part of the talk is how do we design this coordinated many-body phenomena, process information robustly in the presence of ubiquitous noise and sometimes even chaotic dynamics. So that's the motivation, and I've been thinking about these varieties of work, but since today is about quantum machine learning, I'll focus on the first one. So let's focus on quantum information processing. Why do we want to study quantum information processing? to begin with, I think it all began with Richard Feynman, who postulates that if you want to process quantum many-body systems, you better make the processing quantum mechanical, because at the intrinsic level, quantum dynamics are fundamentals, and I'll tell you later that the superposition is one of the key where classically it's hard to simulate. So the beginning of this field was kind of hopeful, and the idea was that if you want to process, for example, a ket psi representing some many-body quantum states, and if you think about simulating or processing this quantum state data or represented on a classical computer, because of the superposition, suppose you have n-qubit system represented by quantum state psi, then classical information requires to store this information will grow exponentially large in the number of qubits that you have, 2 to the n. You need the coefficients in front of each of the bases in this 2 to the n computational basis states, right? So, which means that in general, if you give any arbitrary quantum states of n qubits, the information will grow exponentially large, and as a result, you cannot really just store the information of large many-body quantum systems robustly and efficiently on a classical computer, and thus it's practically impossible to store this information classically. However, on the other hand, if we don't convert these quantum states in the lab and represent them as a classical information, maybe we don't have to care about this quantum classical bottleneck, and perhaps we could just process this quantum information on a quantum device, a quantum substrate, and output what you care about in terms of the information processing, right? But that's the vision of Richard Feynman long ago, and one of his famous quote was that nature isn't classical, so if you want to process it, you better make it quantum mechanical. So rather than having a classical computer to not just store but process these quantum states, you could replace this processor by the quantum processor, and then you read out whatever information is important about the quantum state you care about. For example, you might want to ask if the picture on the left has 2 electrons and what orbits are there. The quantum processor will just say yes or no before you need to extract any classical information about the original quantum states out. So quantum processor could hopefully be used to process quantum data from quantum experiments, and that's the high-level motivation of why we build quantum processors at all. And the final hope is to be able to understand material science of molecules in these quantum experiments could be designed to synthesize new materials. So that's the hope. Of course, when we can build quantum computers, the main question is what kind of processing it can enable, in which classical processor cannot achieve. One of the most well-known algorithm is, of course, the Chor's algorithm, where you could factorize 2 times multiplying each other exponentially fast. That's the so-called Chor's algorithm. You could also do unstructured search with exponential speedup, so-called Grover's algorithm, or you could do matrix inversion using SHL algorithm. And these quantum processing paradigms are already written down clearly in this famous Nielsen and Chuang textbook on quantum computation and quantum information, which is sort of a Bible for the beginners who want to access this quantum computation. It has really nice ingredients explaining how to achieve quantum advantages in this famous algorithm. However, given that the quantum devices can process in a way that the blueprint we designed them. And that means that there's no noise, the coherence time is really long, in which you could operate this large and deep circuit, unitary circuits in a way that can operate reliably with high fidelity. And that's the so-called fault-tolerant quantum algorithm, or FTQC, a fault-tolerant quantum computer. If it can be built, which is the goal of many quantum companies now, if you can build FTQC, then this algorithm can be deployed and you get quantum advantages, provably. However, in the current era, the devices are kind of noisy. You cannot operate unitary evolutions for too long, and the fidelity of achieving what we design. This is not as expected. And currently, we're in the era called noisy interpreted scale quantum, or NISQ era for short. And one of the useful algorithms, which are heuristic in a way, there's no provable guarantee in any way, is the variational quantum algorithm, which is a hybrid between quantum and classical. The idea is that you have a quantum computer or quantum devices to process high-dimensional data. You actually represent the state psi, which can consist of many qubits reliably. However, because of reliability and high fidelity, you need this unitary evolution U of theta to be a short circuit, not too deep, because if too deep, then error accumulates due to imperfection of environments and devices. And as a result, once you can represent this state reliably, you evolve roll through this U of theta into another quantum object code that you could reliably parameterize to extract some information out by taking, for example, expectation value O. And once you make measurements many times, repeat the measurement, you extract this classical information out of that quantum state. And the goal is to create this high-dimensional quantum states parameterized by parameters theta to solve some minimization task, right? So the idea would be use this short circuits, but many qubits evolution on quantum computers so that you don't need to store this exponentially large quantum object, but you could tune experiments in such a way that you can control the unitary quite well. And there's a variational parameter theta that controls how the quantum state is parameterized. And the goal is to optimize this parameter theta so that the readout can solve some optimization problems. And you keep iterating this in a loop until you converge to some state U of theta star that solves some hard to optimize problem. This is the so-called variational quantum algorithm. In a way, you use quantum computer to generate hard to store classical information by using quantum data and vary this parameter theta to solve how to optimize problems. So one of the proponent of this idea was by IBM, which was published in Nature in 2017. They were showing that to search for ground state for 2 or 3 atom molecule could be achieved by this task if you design a loss function as the minimum of the expectation values of the Hamiltonian. In that case, you are quote-unquote searching for ground states, and then you could find ground states in simple molecules like this. So it seems like a hopeful approach in a way, because you could really use a quantum simulators to simulate and find ground states. And if you can solve this problem for large-scale system, then material science and pharmaceutical companies would have a new way to think about creating new chemical molecules, right? And after that paper came out, it was a really nice example of doing optimization with variational quantum algorithm, and there are applications in various fields because some of machine learning models is also via quantum optimizations, find some sort of minimization of the loss, and you parameterize quantum state to solve some hard to solve quantum machine learning task, combinatorial optimization, searching for logistic optimization solutions, and so on and so forth, as shown on the lower right. However, that was the peak of optimism. The question is, can we actually gain quantum advantage? That question requires you to scale up the system size. And here is the reason why we start to be pessimistic. If you think about optimization is in this high-dimensional loss landscape, in high dimension in a number of parameters, here are the examples of what people show. If you want to train this model or find or optimize data, you would need to be able to extract the value of the loss function out with sufficiently featured loss landscape, because if the loss landscape has no gradient, then you cannot do gradient optimization, and as a result, you cannot train. This is what they show on the upper right, and is typically find in this modern days version of quantum algorithm training. In order to train, the loss must be sufficiently featured, And the smallest number of qubits, which is the case for what IBM did and what Google showed as well, in terms of solving VQA for some ground state optimization. For the small number of qubits, it seems reliable. The gradient of the loss, average overall initialization data, is sufficiently featured. Gradient is not small, but as we increase the system size, number of qubits in this case, the loss landscape become more and more flat. So the gradient in any direction on average for any random initialization of data will be vanishing. So in this case, they call this phenomena barren plateaus because it's a plateau in the sense that the loss landscape is flat and it's barren because unlike in the deep learning where local minima can be saddles, there are still directions where you can escape from the saddles. But because it's the plateaus in all directions, the variance of the gradient is kind of zero. So it's barren in that case. There's no single direction that allows you to go downhill on average over theta, which is kind of severe problems. And people in the community now are starting to understand the emergence of barren plateaus is in fact the curse of dimensionality in disguise. The statement about barren plateau is that on average, if you parameterize your quantum circuit by your theta and this dimension of number of qubits is large and there's some strong entanglement and so on, it explores the Hilbert space quite uniformly. And because of that, the variance of the gradient of the loss will be exponentially small in number of qubits. And the intuitive reason behind that is because of the expectation value result. Because if you think mathematically, what does measurement to get a sample expectation value O means? It's basically the inner product between rho and O. You can write expectation value of O's in terms of trace of its D matrix parameterized with data and times O, and that's the inner product of some sort. And when your density matrix explore Hilbert space fully with large dimension, you think of this as some sort of random dot products between exponentially large vectors, which means that the inner product most of the time will be zero, and as a result, you get the so-called exponential concentration phenomena or the curse of dimensionality. And that, on the one hand, you want to go into a large system size so that basically you cannot store that information. But on the other hand, in order to train this model and take advantage of large system size, you need to be able to resolve this inner product and reliably reconstruct the loss function, which is not feasible. And people have been thinking about how to avoid barren plateaus because if you don't know how to avoid them, you cannot really train, and as a result, VQAs or variational quantum algorithm becomes not very useful when you increase the system size. One of the work that we have recently thought about is that there are many strategies to do the so-called warm start. For example, if you want to find ground states of some molecules and you initialize your ansatz close enough through parameterization theta star of some ground states, then people have shown this warm start strategy is that within certain regime around that local minima, if you initialize close enough, you can actually find gradients and train and optimize. But you need to be warm start, which means that you need to be close enough to the ground state. And there are many proposals to propose how to do that, and many circuits have been proposed, and there are some strategies like the identity initializations and so on if you work on warm starts. What we show is that within this typical ansatz, which includes those favorable for chemistry, finding ground states, you could do tensor network types of states. If you are polynomially close within any local minima, this green area we call patches, polynomial in the number of qubits, then you have a chance to find gradients and optimize. So it's kind of somewhat positive and somewhat negative results. It's positive in the sense that you don't have to be exponentially close in the parameter space to begin with. If you need to be exponentially close to the true minima, then it's kind of hopeless when you scale up. But on the other hand, the bad thing is that the bad news is that you need to be polynomially close, which means you need some sort of clever initialization to begin with to guarantee it's trainable. So that's one of the way that gives some hope in terms of BQAs. If you are using some sorts of answers and cleverly guess initial conditions that are polynomially close to the true global minima, then barren plateau will not be there. But if you blindly initialize the parameters, then you still suffer from barren plateau. And another approach, rather than using this gate-based time evolution to think of BQAs, when you think about analog time evolution, that's more general than unitary updates, in the sense that it's much closer to what the hardware experimentalist can perform. So you can quench a series of whatever experimentally feasible evolution during different times to create BQA's ansatz, and there are more freedoms to control this time evolution and more natural. So what we show is that if you, of course, intuition carries over if you are in the phase of matters when the time evolution explores fully the Hilbert space, such as the thermalized phase, then barren plateau will be a problem, the lost landscape becomes flat. But if you are in the many-body localized phase in each of the quench, because MBL is kind of restricted to certain symmetry subspace and doesn't explore the Hilbert space fully, then the curse of dimensionality can be somewhat bypassed. And that's what we show if you initialize in MBL quench, but the number of the depth of the evolution is long enough, you could reach somewhat high expressivity, and at the same time, initial trainability is guaranteed. So if you have experimentalist friend want to do BQAs on analog devices where they can use different sorts of Hamiltonian interactions to control time evolution, then optimization using many-body localized phase would allow them to train. And if they can quench this long enough, finally it will converge with some good solution. So that's what we show in this paper. That's the story about variational quantum algorithm, and barren plateau was really the problem. The way around it is for the analog system is to think about many body phases that don't explore the Hilbert space fully. And in the digital system, you can think about the warp start strategies, how to initialize them so you can follow up with the trainability. And after BQA suffer from scalability barrier due to curse of dimensionality, there are other quantum machine learning algorithms that has been gaining recent traction. Two of them are quantum machine learning machines and quantum reservoir computing, and this can be categorized as a non-variational quantum algorithm. Unlike in BQA, where there are parameters corresponding to some experimental knob in the quantum operations, here the quantum dynamics are somewhat fixed. The parameter will be fixed, but what's different is you train the readout, which I'll explain shortly. So the question is, if BQA suffer from trainability, can non-variational BQA, non-variational approach scale up and gain some quantum advantage? So that was the question that many people got interested in this non-variational approach. So let me explain this paradigm. So quantum extreme learning machine is also a special case of quantum reservoir computing. So let me explain quantum reservoir computing. The idea is that you have some sort of natural quantum dynamics happening in the lab. For example, theoretically, that would correspond to a Hamiltonian evolution where the parameters in the Hamiltonian is fixed, no variation of parameters in the Hamiltonian. But then you think of this natural evolution as being driven by an input data. And the input data drive will lead to the responses of the quantum substrates or the quantum reservoir in this case, given that by the quantum dynamics. And if the quantum dynamics respondingly to the input drive differently and rich enough, what you read out of this response function on your quantum substrate could be used to say something about input data. So you extract some output out of the quantum response of the input drive and then do some prediction about the structure of the input data. You could do static classification, or you can do temporal time series prediction. And the nice thing about this approach is that there's no variational parameters in the quantum dynamics, and all training appears to be in the linear regression in classical post-processing. And this is exactly trainable model. So there's no trainability barrier here. And just to show you that this approach worked, in fact, it was motivated from the classical residual computing. People designed a large recurrent neural networks that was initialized near the edge of instability, and they fixed the parameters in the RNN. And then once they used this response of near edge of chaos reservoir as a way to encode the input drive, you could drive the system, for example, in the top picture, which is this even spatial temporal chaos nonlinear programmable Ziermachinski time evolution, where the vertical axis is the lattice. There are, I think, 22 or 23 or 24 lattice here, and on the horizontal axis is the time. So the top one is the target time evolution, and if you train this quantum reservoir classically well by reading out the response of the input drive, it can even predict the future of chaotic spatial temporal chaos like this quite accurately, up to about 5 to 6 years of time, as shown by the arrow in the bottom panel. And because of that, people think about why don't just use quantum scrambling reservoir, because the whole idea was using neural networks near the edge of chaos is that once you're near the edge of chaos, any tiny response would lead you to some high-dimensional representation in terms of network activities. And from this high-dimensional response, you can build a feature map in the machine learning sense to do predictions. So because of quantum superposition, any tiny variation in the input could be expanded into the high-dimensional superposition in the Hilbert space. People then use some sort of high-dimensional dynamics, scrambling dynamics in particular, as a quantum reservoir. And with only 10 to 20 qubits, you could predict already very accurately chaos in Lorentz butterfly, as shown on the bottom. So natural question is, so if you scale up this idea, would you be able to get some quantum advantage? There has been work that shows that to achieve same accuracy as recurrent neural networks of about 10,000 neurons situated near the edge of chaos in some particular benchmark task, it requires only about 20 qubits for the scrambling and chaotic reservoir. Natural question is, would this really scale, and will you get some quantum advantage? And if so, what is the function that this quantum reservoir computing will compute? To abstract away this high-level talk and high-level discussion I gave, here is the structure of the quantum reservoir computing. You have in the red part at the lower left, that's the qubits in the system that will encode the time series that drive the dynamics, and the hidden parts shown in green you couple to the red accessible qubits through some unitary evolution, typically some chaotic or scrambling dynamics to generate high-dimensional feature map, and just to make sure that any information from input drives get passed over to the larger dimensional Hilbert space of the coupled system. And on the lower right, there was the sequential updates of this new data comes in, couples to the unitary block U that couples both the hidden and the accessory qubits. And when the new data comes in, the accessible qubits get refreshed and keeps evolve like this until the final time step. Eventually, you take out the expectation value reads out, and from this reads out, do linear classification, which is exactly trainable to do some time series prediction. So that was the mathematical structure behind this quantum reservoir computing. Of course, if you think about high level, the object that leads to the curse of dimensionality or untrainability in VQA still exists here. Here, the readout is still expectation value. So if you can borrow the same intuition that if rho is really high dimension on average, then on average, this expectation value should be near zero because it's in the product between two large vectors in the Hilbert space. And this is the work that we show. In fact, even though the two models, both extreme learning machines and reservoir computing, is exactly trainable, no scalability problems for training. But what we show is that it leads to a generalization error. The models become input independent, which is kind of like you predict random labels rather than predicting reasonable signals. And just to go into some detail, so it's not too much of the high-level talk, I will just focus on quantum machine learning machines to get some ideas what this kind of function can compute, and if you want to get common advantages, is it possible to have no curse of dimensionality and this kind of discussion. Okay, so let me get into the detail of the first paper, quantum machine learning machine. I will explain to you mathematically what quantum extreme learning machine computes, and if you want to aim for quantum advantages, what kind of metric we're going to use, and can we avoid the curse of dimensionality. So here is the mathematical setup of quantum reservoir computing, which is more general than extreme learning machine, but later on I will specialize to extreme learning machine. You have an input drive, which is a vector in the dimension x of k at time step k that comes in. And this input drive at time step k will interact with the state of the reservoir, or S, at the previous time through some nonlinear function R. And through that interaction, it gives rise to the new states of the reservoir called S of k at the new time step. The incoming inputs come in at the current time, interact with the state of the reservoir, leads to the new states of the reservoir. And you keep iterating this until you eventually take some time series readout of the states of the reservoir, typically by some linear regression through the weights W, to make some prediction. And some of the prediction is to predict the next time step of the input time series. And this can be quote-unquote trained to optimize the weights of the output by just simple linear regression with some regularization parameters lambda. And W can be solved exactly, and if you construct this matrix W exactly, then in principle, you should be able to reconstruct the time series that drive the reservoir. And in the extreme learning machine, rather than iterating through many steps, you have only a single time step, which is static classification. For example, the input could be a different MNIST figure from number 0 to 9, and the output would be just classify which class these input drives belong to. And the training is the same. Rather than accumulating all the time series, then we predict just one class. Okay, so this is the general extreme learning machine. For quantum extreme learning machine, you change this nonlinear interaction R by some quantum evolution. And the readout is the expectation value readout on observables that you can measure to be O observable O1 to observable M. Who cares about, and eventually you train this W to predict the function corresponding to the input. The natural question is that from this framework, what kind of function f of x can this paradigm compute in terms of the quantum evolution? So to understand that, you can partition the abstract picture I told you about in terms of mathematical representation. You can have accessible qubits, which encode the classical data by some unitary encoding as a function of x of the inputs. And through that, you couple with only one time evolution with the reservoir evolution through this UR with the hidden qubits also. The result is the M values of expectation value. So to understand what kind of function these things compute. In the end, it's just the linear combination of observable. So the prediction will be f of eta as a function of x, and this a linear combination of observable of x. So the question is, what does this expectation value of O that we care about can be represented in terms of some simpler function, so that you can decompose the complexity of this function in terms of something you know about the structure. So the data encoding, in order to compute this expectation value of O, data encoding start with some initial density matrices, rho of 0, then the u of x, times rho of 0, then u delta x is the rho of x, and rho of x will evolve through this reciprocal evolution. So that's the blue line shown in the middle. And eventually, this expectation reads out. So you can combine these together to know what kind of function it computes and how expressive is this. You can show that description from this representation gives rise to linear combination of Fourier modes as a function of x. And the natural question is then, how do you define and how do you know how many modes are available? Turns out the encoding unitaries determine how many modes you have, and the number of modes depend on the spectral gaps of the Hamiltonian. And there's also so that's the modes it depends on how you encode the system. If your system, if your encoding unitary can encode a variety of gaps, then the number of available modes will be large. But even though you have number of available modes, you need to ensure that the amplitude of those modes are non-zero. Otherwise, if the amplitude of the modes are zero, then those modes are no longer accessible, even though they are available before. And it turns out that this amplitude depends quite complicatedly in terms of the overlap between the reservoir evolution to the observable at the readout. So in order to expand this out, you can just plug in what I showed you earlier, and you find that the expressivity of these modes depend on a few parameters. It depends on the number of observable you take out, and depends on the number of modes available and the number of observable m that you care. And typically, if you want to classify what is the minimum number of available modes are there, how expressivity there are, there will be the minimum between these three values in the bottom are usually the first two, because in principle you cannot measure 4 to the NO number of ICP-OVM. So we just care about only the first two, which is the number of modes due to unitary encoding, as well as the number of observable M. Right. So you want to maximize this number of available frequencies. So one strategy is not to do Pauli reuploading. Pauli reuploading is a simple way to encode Hamiltonian, where each of the qubits you encode with the same Hamiltonian. In this case, you have only about linear number of modes in the number of accessible qubits. But if you encode with, for example, exponential encoding, where each of the qubits you encode with different factor of Pauli x times some structure coefficient beta k, then you can have exponentially many frequencies in the available modes. So you want to be in the high end. You want to encode the system through exponential encoding rather than the standard Pauli reuploading. And of course, that's one thing, that's the number of available frequencies, but you need to make sure that the amplitude itself is also non-zero. And to guarantee that amplitude is non-zero, you need to make sure that the overlap between unitary evolution, reservoir evolution, and observable is non-zero. And this intuition carries over if you have a complicated reservoir evolution, then the number of available Fourier frequencies will not overlap. Or you want this reservoir evolution to explore a large Hilbert space so that the overlap between O and UR are not zero. If there's no evolution at all, then the amplitude will be 0. So that's shown on the right figure here. Of course, then what we're just thinking about is why don't we just scale up the system size, right? And just use exponential encoding together with reservoir to explore the Hilbert space fully, so that the accessible modes becomes large and they overlap to get the amplitude are non-zero. So that's the famous hippo from Thailand. He would be optimistic and just say, let's grow up and be expressive and scale up system size. Okay, but now there's a catch, right? That's what I alluded to earlier in terms of the curse of dimensionality. So let me remind you of what exponential concentration is, for those of you who know. So we say that expectation value O as a function of x would concentrate exponentially in a system size towards an input independent value, which means it's independent of x. There could be this concentration in two ways. It could be deterministic concentration, where the deviation from this input independent value mu becomes exponentially small deterministically. Or it could have some chance to deviate away from this input independent value mu with the exponentially small chance. There are two ways to get this concentration, which means that to actually resolve input dependent value x, you need the number of measurement shots to scale exponentially large with n in order to resolve anything meaningful about the value x, right? So that's central limit theorem in disguise. And this actually led to barren plateaus in VQAs, in quantum kernels, and also QLM and QRC, which we show in this work. It leads to, even though trainability, but it leads to generalization error, because model become input independent. Even though it can be trained, it's predicting something independent of x, unless you have exponentially large number of measurement shots to resolve the signal from noise. Okay, and there are four sources of exponential concentration. You can have a strong expressivity. That's the intuition for curse of dimensionality, because if you have high expressivity, you explore the Hilbert space fully, and then the concentration becomes severe because the linear product is small. And you could have global measurement-induced concentration as well, for the same reason, entanglement induced concentration. And also lastly, if your reservoir is kind of noisy, you can have a noise-induced concentration. So these are the four sources that leads to exponentially concentrated output that becomes input independent. This is just to show you exponential concentration in practice when we have this type of circuits. So if you want to see a mathematical proof, you can check out the paper on the top right. But the summary is that to get quantum advantages due to the expressivity of the function f in QALM, we know that doing exponential encoding allows exponentially many frequencies in the Fourier modes, which is not easily classically simulable. And to achieve that, you need the Fourier amplitude to be non-zero as well, and that arises when you have the reservoir that explore the state space fully. So you have high expressivity reservoir like chaotic icing, random, and all these things. But it comes with a cost of exponential concentration, because to get quantum advantages, you need to push up the number of Fourier modes you can have, but that at the same time comes with the cost of the number of measurement shots you need to scale exponentially large with the system size. So it's kind of similar story to VQAs in a way. You want your system to be larger and more expressive, explore the Hilbert space fully to make sure classically it cannot be processed. But at the same time, problem comes with when you need to make the measurement out of it, you need exponentially large number of shots due to the exponential concentration phenomena. So that's a quantum to classical bottleneck. The quantum parts you need high dimensionality. And the classical parts, when you take a readout, because of high dimensionality, you get curse of dimensionality, and you need exponentially many shots to resolve them. So it's kind of a tug of war between having high dimensionality to get quantum advantages. At the same time, it's costly to measure and gain those true advantages. So somewhere that could be useful is not to have an exponential number of Fourier modes. It could be this polynomial in the Fourier, but the degree of polynomial is large enough to make sure that you can sample with reasonable resources. So the story of NISQ machines up to now apply to both VQAs, which is variational approach, and non-variational approach like quantum kernels, quantum machine learning machine, and quantum visual computing, is that on a small scale device where you could run on Qiskit or even simulate on your classical computer, it seems promising to solve machine learning. But to actually think about quantum advantages where superposition allows this exponential separability, we still don't know how to actually scale up without the curse of dimensionality too well in most cases. Okay, so one approach to get away around that is first, you don't care about noise, you don't care about short noise, you can make everything ideally and be naive and optimistic like this guy and work in the assumption of fault and quantum computing at TQC. Then you can crunch out a number of quantum machine learning algorithm or quantum simulation algorithm with polynomial speed up, exponential advantages, and so on and so forth. That could be done, but that's too optimistic. If you want to be more realistic, recently we have been thinking about bypassing this quantum to classical bottleneck. All these plateau and curse of dimensionality comes from trying to estimate expectation values without of observables of the high-dimensional quantum objects, and that's the quantum to classical data conversion problems. One way to bypass that is to somehow have machine learning models when you don't need to make measurement too much until you have done all the processing already. For example, if I think about input quantum phase of matter in and ask, is this the correct phase of matter I care about? Rather than taking expectation value reads out, there might be some clever way to train the model and spit out the correct phase of matter. So that's the idea. You can probably bypass this quantum to classical data conversion, which suffers from the curse of dimensionality, by designing another paradigm of quantum machine learning, and that's what we have been thinking about in terms of fully coherently train the models and process it and measure once only when you want to know the answer. This is what we coin as autonomous quantum machine learning, where you have the data set and feed into the quantum models parameterized by the theta initially, and beta is the structure of the model. And rather than taking quantum measurement to get feedback loops to create this function A of theta star, there might be a way to bypass quantum measurement, to bypass this curse of dimensionality and get the right model out. This kind of process we formalize as autonomous self-training, QML. And so one possibility is to think about trying to optimize for unit 3 evolution that maps your classical or quantum data into the correct answer, and you make measurement which spit out the correct answer that you care about without estimate expectation value reads out. So one way to do that is through the so-called Riemannian gradient optimization, because Riemannian gradient is some sort of a natural way to coherently process gradient dynamics on quantum computer, has been popularized lately due to a so-called double bracket quantum algorithm, where you optimize some sort of optimization problem on the unitary manifold coherently. So by being able to find the gradient coherently on the quantum devices, then we can bypass finding gradients through estimates of the expectation value reads out. So this is what we propose. We were going to use Riemannian gradient optimization as a way to realize autonomous self-training QML. And from that, you can compute, for example, the Riemannian gradients, which is a function of the current state that you have, and hopefully you can update this unitary to reach a unitary that minimizes the loss function that you care about. And this turns out to work well for some particular tasks, for example, shown on the bottom here, where the idea is to try to classify unseen quantum states correspond to the ground states of the Hamiltonian on the lower right. And this Hamiltonian has some sort of complicated looking phase diagram corresponding to either topological phase of matter, in this case they call Haldane phase in blue. We have anti-ferromagnetic phase in pink, ferromagnetic phase in red, and cyan, which is a trivial phase. Question is, can we solve this quantum machine learning task of classification, spit out the correct labels for phase where it has never seen before, and train everything using Riemann gradients? What we show is the ingredient to do that. Here's the loss function, Riemann gradient, and updates unit tree. You update your tree not for too long, and you can construct the training data with only, in this case, 5 training data. Each are sampled from different corners of different phases. And with this 5 training data shown in the cross, here you could actually reconstruct other phase diagram relatively well, as shown on the right. So here is a reconstruction on the right. It has only seen 5 data points, and it is asked to spit out what is the correct colors of the input ground states corresponding to that parameter space. So it kind of do well within the boundary phase. Of course, there'll be some finite size effect near the boundary that there will be some incorrect predictions. And as you can see on the left, the loss function kind of reduced quite fast in only 10 iterations using Riemann gradients. With step size s equals to 1, the loss is kind of gets smaller and smaller relatively fast, and can reconstruct the prediction of unseen data quite accurately. And this can be done without any classical to quantum data conversion in between during training at all, because of this generic way to find gradients coherently on the loss landscape. So the trick is just to come up with the correct loss function and then apply Riemann gradient. And if you can find that loss function, in this case it can be done, then you get natural optimized U that for any input unseen data row, it will spit out the correct labels of that phase for you. However, there will be some debate about this task because some people show that it's classically simulable. So even though we show it can be done coherently on the whole quantum devices, this phase classification problems still can be done on a classical computer. All right, and it was quite nice in a way because, for example, the training here, we only use one-step training, only use 5 data points and can actually reconstruct the whole phase diagram, which is kind of remarkable. But in fact, in the paper that we are writing, there's some caveat to this approach, and it turns out to be a data set that use some structure of orthogonality in which the Riemann gradient approach figure out by itself. So the preprint should be online within, I don't know, in the next 2 or 3 weeks. So stay tuned on that if you're interested to think more about not just Riemann gradient descent, but the framework for autonomous quantum machine learning, where there's no problem with quantum to classical data conversion during training. Okay, or the last option, if you don't want to think about the autonomous quantum machine learning and somehow can do quantum machine learning or scale up with the presence of noise, is to look for inspirations where noise is known to help do computation, and that turns out to be the brain. So I've been thinking about inspiration from neuroscience, and there have been experiments in neuroscience to show that certain parts of the brain and certain computation tasks can benefit from having background noise. So I will not talk about this since it's not about statistical mechanics of learning, but the final goal is to extract mechanism from what is hindered from biological intelligence and potentially design similar quantum mechanisms that can harness noise for computation. So into the unknown, I think it's kind of exciting now. We don't know what we're going to do next, so we can ask a question: how can we use noise and chaos for quantum advantage, and potentially for quantum AI? So some inspiration would be to study biological systems, which is kind of really messy, like the brain or collective population dynamics or whatever, that seems to be so robust despite change environment and extract ideas to build quantum algorithm to mimic that. So that would be kind of research program that I'm hoping to push forward. I wouldn't talk too much about this, but I think it's kind of just to show that this intersection between statistical mechanics, learning algorithm, either from neuroscience or neuroscience, and many body quantum physics is kind of fruitful, and there are many ways we can use noise and statistical mechanics idea to build or even try to understand quantum algorithm. And for the interest of time, just to advertise that I'm moving to NTU in November to build up this group called Physics of Information Processing and Complexity, where we will push this exploration of studying biological intelligence and also explainable models for artificial intelligence, and hopefully build a quantum algorithm that can coexist or even harness noise computation. And if you're interested for PhD positions or postdoc, I'll be happy to discuss if you want to explore this direction together. And lastly, I'd just like to thank my close collaborators. I think we work very closely with Thiparat in Chulalongkorn University. He was a postdoc of Troy Holmes at EPFL, so we have some ongoing collaboration like this autonomous quantum machine learning. There are some really talented students in our group and that will move on to study abroad, and neuroscience work that we are exploring together with So that's the end of my talk today. So I'll take questions. Thanks for your attention.
Okay, thank you too for your talk. It's very useful and very hot topic these days. So any question for Thiparat? Here we have the first question in the chat box. The exponential concentration occurs for all types of quantum circuits. Are these classes of circuits for which this phenomena does not arise? Yeah.
Okay. These class of circuits for which this phenomena arise? Yeah. So there's a nice paper by Thiparat and Zoe and Marco Scherzo, who wrote I think now in Nature Review Physics, does classical simulability implies trainability, something like that. Does the absence of baryon plateaus implies classical simulability? So in the BQA circuit, in digital version, the answer is some sort of yes. So if you can have many circuits, which is very simple. I can give you an example. You can have just product states, right? If it's a product states, then you can easily train and so on. But then the problem is that you can classically do it on a classical computer too. There's no need for a quantum computer to generate entanglement and high-dimensional representations. So the short answer is yes, but it comes with the classical simulability problems. So I think the nice way to think about this is probably start with the circuit that is not fully entangling, doesn't exploit the Hilbert space fully. In other words, not too expressive and not fully exponentially large Hilbert space expressivity, but maybe polynomial large. That people that think about equivariant quantum neural networks where the dynamics can be decomposed into different dynamical algebras, and that you can control how many of the dynamical algebra blocks you want to keep. And I think if you have not exponentially large Hilbert space, but polynomially large in a way that you can sample enough to get rid of, then it's still reasonable to use quantum computer. Yes, and the other way is, as I say, even though you get exponentially large Hilbert space, trying to find initialization that works for warm start, that is also interesting. Yeah, but in short, yes. So you get classical simulability if there is a guaranteed absence of Variational particle. So there's no need to build a quantum computer to begin with. And people in that direction can simulate this quantum circuit using tensor network types approach. There are many well-known algorithms to build tensor network diagrams and computation to simulate those quantum states.
Yes, someone is raising their hand, so please open the mic.
Sorry, can you repeat?
Yeah, hello.
Hi.
Okay, yeah. So, thank you, sir, for the informative talk about quantum. And I have two questions. First is about, as you mentioned about the QELMs use fixed circuits, non-changeable parameters to avoid the variables. In practice, different circuits generate different feature maps, and the circuit choice seems to matter significantly. Is there any theoretical guidance on which fixed circuit structure leads to more useful features map or a given distribution, data distribution?
Yeah, right. No, that's a good question. So let me flash back the slides a little bit. There was this slide I probably went through a little bit fast in terms of what kind of feature maps the reservoir that QELM computes was basically this, actually. So if you look at the function, my mouse doesn't show up here for some reason. So f of a of x is what this QELM computes. And as you can see, the a of omega of k depend on the circuit of the reservoir U. So if your U is not scrambling, it's only explore a tiny corner in the Hilbert space, means that most of the overlap there will be zero, which means that it will reduce the number of accessible Fourier frequencies. That's what we see here. So for example, if you use no reservoir at all, then the Fourier richness, which measure how many non-zero coefficient of the Fourier modes will arise. If you don't use any reservoir at all, and if you increase the system size, most of the amplitude will be zero, so it's not useful. And the reservoir or the circuit that would allow you to have as large number of Fourier frequency as you like is to have a chaotic Ising or high random, right? So that's the top line. However, this comes with a cost, because in the end, you show that with perfect measurement precision, you get perfect this large number, exponentially large number of Fourier modes. But at the same time, the cost is really this exponential concentration phenomenon. So you have circuits that are really expressive, or high random, chaotic, or whatever. But in the end, the readout would be input independent exponentially as you increase the system size. So that's the trade-off. So that's why I say maybe you use a reservoir that do not fully mix or fully scramble all the quantum observables, but something in the polynomial corners where you can still sample enough polynomial to resolve the input dependent output.
Damn.
Oh yeah, clearly. And one last question. Are you aware of any training-free matrix that could predict the encoding quality without actually running the quantum evaluation? And similar to how the neural architecture search using the process metric like gradient norm or self-flow to avoid the full training.
Sorry, can you repeat the question again? I didn't catch that.
My question is about are you aware of any training-free matrix that could predict the encoding quality without actually running quantum evaluation?
I'm not sure. Like there's a training. What is gradient-free training and encoding? What? How is it related? I'm not sure. I understand.
The metric that did not require the full training like the optimization in the VQC. We just use some proxy metric for the rescreening. Yeah.
I'm not sure if I understand you saying that. Is there a way to not train and or you come up with a metric where it doesn't suffer from training? Is that the question?
Yeah. I mean, he want to ask about the trainability of quantum circuit. How do we measure the trainability of some quantum circuit?
So what I mean by trainability, you can think of very similar to classical neural networks. You have a loss function, right? And if you could somehow change the parameters in such a way that you eventually goes into, for example, the local minima in the green patch there, that's what I call by trainable. It doesn't have to be gradient. It can just be any search, right? But the problem with this PQC trainability is that if you want to train in this PQC, one of the ways to gradient, but the gradient is exponentially small, which means that most of the time it's flat, which means that you cannot find a true global minima or optimizing for data star that minimize the loss. So by trainability there, I just mean there's a procedure, either optimization with gradients or non-gradients method to search for data star reliably. And when I say non-trainable, it means there's no such approach. Because if you actually have current plateaus, it means that the loss landscape becomes exponentially flat. The feature is very, very small. So there's no way to distinguish between the loss value between data 1 and data 2. So that's what I mean by non-trainability. But as I said, later on in quantum machine learning and non-variational approach, it can be trained because I show this weight optimization algorithm, but the curse of dimensionality will manifest as ungeneralizability of prediction. With models, even though exactly trainable, the output becomes input independent. That's the other thing. Yeah, but in short, for trainability, if you have expressive circuits, PQC, in BQA, then you go to Bram plateau. And you can just look at the small circuits and not expressive circuits, and then there'll be guaranteed trainability. Only recently, people show this kind of statements where the loss become non-flat if you use not expressive but useful circuits like tensor network and matrix product states as a way to parameterize PQC, and then they can show that this Bram plateau problem is not too serious.
Yeah, okay, thank you.
And some students interested in quantum machine learning, and they want to ask how to start with the quantum machine learning, like how to do study first, or how to start with machine learning currently.
Good question. So how do we do quantum learning? Is that a question? If you want to pursue advanced research in quantum machine learning. Okay. I guess there are some key papers now, right? So you can think about fully fault-tolerant quantum machine learning algorithm, and that can be done, but as I said, it's not really in practice and can be implemented. You can start just reading papers and come up and learn new tricks of how do you use quantum algorithm with different primitives, and different primitives quantum algorithm would have some certain speed up. For example, if you want to encode some nonlinear function into the unitary evolution, you can do quantum singularity transform. Now there's quantum eigenvalue transform, and so on and so forth. Just think about breaking down quantum algorithm into primitives, and think about what machine learning algorithm requires as a different primitives, and then we combine them in a certain way to show advantages. But that's one way for the fault-tolerant algorithm. For implementable NISC devices, there are some review papers on quantum machine learning or variational quantum algorithm. You can take a look into that. And I personally like Penny Lane. I'm not sure if you have read this website. It's by a company called Sanadu that creates the online platform on tutorials and learning, not just about quantum machine learning, but quantum algorithm more generally. It can be explained very clearly. So I also encourage many students to, for the first time that they're starting to quantum machine learning, look at Penny Lane website. They have some tutorials on that.
Yeah.
Sorry, but I mean that I have learned the basic of quantum machine learning pre-skit at Penny Lane, and I want to pursue seriously in quantum machine learning research and make publication, write papers. So I wanna ask for a career path. For example, I can join the program in the program in doctoral, for example, to study and research deeper in quantum machine learning.
Right. So there are a few groups that focus on quantum machine learning and quantum information processing. So I suggest you can reach out to those groups directly. And for example, like Zoe Holmes group at EPFL, there are groups that work on quantum-inspired machine learning, like Juan Kraskila in ETH Zurich. There are groups in Edinburgh on quantum software lab. Mina Dosti is doing some quantum machine learning. I think if you look at research papers recently and then search for variational quantum algorithm or quantum machine learning machine, blah, 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 you see that those groups are those that are trying to push the field. So one suggestion is to reach out to the groups that work on the area that you are interested in QML, and then try to communicate with them. So I know I'm moving to Singapore. There are a few groups doing quantum machine learning. For example, like Millet Gu at NTU is doing that with Jane Thompson, and I will join force with them on quantum machine learning and some other aspects of physics of learning. For the fault-tolerant quantum algorithm, you can look at Patrick Ribbentrop in CQT in US and Singapore as well, that are leading this kind of effort. So I would just advise you to reach out to them directly, or the other way is to look for like summer school. There are usually summer schools. In Europe, they have EQAI summer school, and the famous ones is the Los Alamos ones. So that's where the Barron Plateau camps was born. People discover about Barron Plateaus and build up theories around that from Los Alamos. And I think there are also conferences you can go to get to know people in the field. Like QTML is one of the flagship. It's kind of like New Rips and ICML for quantum machine learning. And this year, I think the deadline of application for submission is a month from now. Actually, this month, sorry. So QTML is another flagship. So if you go there, you get the overview, picture of the field, what people are trying to solve, and get to know the community.
Well, thank you so much. And can I message through LinkedIn or any other social media to get
sure.
any advice from for example, to get the link to contact to those groups that you have mentioned before?
Sure. We can email or we can LinkedIn. Yes.
So is there any social media that I can contact you? For example, your LinkedIn or your email.
So, sorry, what's the question again?
They want to ask your social media Tip also has a personal website, so you can just Google his name and you can find any contact information about Tip. Yeah. Don't worry about that. You can just if you want to do it with the machine learning, you can just apply to Tip group, and if you get accepted, yeah, that's fine.
Yeah, so that's, I think like different groups want to work on different things. For me, I have a few set of problems I want to solve. Like one of it is this autonomous quantum machine learning. Real-linear gradient is one way to do it, as I say. And also want to think about how to not just read out data reliably, how do you encode data into the quantum states from some drives. That's also interesting problems that I've explored. There's also this notion of complexity of quantum simulation, through log complexity, and so on. I think this kind of intersection between complexity of simulating quantum dynamics and how that translates into building quantum machine learning algorithm is also what I'm interested in. So if you are interested in this area, please feel free to reach out.
Any question?
So there's I'll send you the website and maybe summarize my group a little bit better than Google Solr is kind of scattered because I've been working on a few things, but it's kind of research focused. You can take a look into that. Yes, CQT also has internship programs. Yes. I think Chuang is doing it now, right?
Yeah, very. Yeah, so if nobody has another question, so we can end now. And thank you again for Thiparat Chotibut for his talks. Very good hot topics nowadays in quantum machine learning, and hopefully you guys can learn something from this talk.
Thanks so much for the invitation again. I'm sorry it's been quite late in Vietnam, I think.
Okay, see you again.